to page 5, 6. We're going to do page 5, the last part of page 5 and 6 together because they deal with tangent planes and level surfaces. So suppose S is a surface. All right, so that's what we have in blue over here with the equation f of x, y, z is equal to k, and let P be a point on that surface. Let C be any curve that lies on the surface S and passes through the point P. So again, here you see C. Oops. So here we have C on our surface, and P is on that. And recall that we can write the equation of this surface as a vector function of x of t, y of t, and z of t. And it means that we can let r at our initial time to be x sub 0, y sub 0, and z sub 0, so at our point P. Since C lies on S, any point x of t, y of t, z of t must satisfy the equation of S, that is f of xt, yt, and zt is equal to k. So all we did was we kind of used parametric equations. We substituted in, for our function x, y, and z, where x, y, and z are defined by t, and that's going to equal k. All right. Now, if x, y, and z are differentiable functions, if we can, differentiate this, then what we can use is we can use the chain rule on this. And so again, the chain rule is I'm going to go through f to get the t. So in order to go through f, I have to go through x, and then to go to x to go through t. The same thing to get to t through y and through z. Well, if you notice, once again, it's multiplication, and they have sum and multiplication, so we can write this as the terms of a dot product, where, dx over dt, dy over dt, dz over dt is just going to be r prime of t, and then the partial of f with respect to y, partial of f with respect to y, and x and z, that's going to be the gradient, all right? Because that's the partial of x, y, and z of our function. So now we can rewrite the equation as the gradient of f dot r prime of t, which is going to equal 0. And in particular, if our dot product is going to give us 0, especially at the initial point, then what we can say about the gradient of f is that the gradient of f is going to be perpendicular to the tangent vector, which is r prime of t. And if we're perpendicular to the tangent vector, then we have the vector that is orthogonal. And if we have the vector that is orthogonal, then we can write the equation of a tangent plane, where our gradient of f is going to be our orthogonal vector. And we use that when we're writing the equation of a plane times, x minus the initial point, y minus the initial point, and z minus the initial point. So we can write the equation of a tangent plane to the level surface just using the gradient as our vector that is normal to our at our point, and again using the point to help us define where our plane is at. Also, for the normal line to S and P is going to be the line passing through P and perpendicular to the tangent plane. So symmetric equations for the normal line are going to be, so again, this is going to be important. So this is the equation for the normal line, and this is the equation for the tangent plane. All right, so we're going to use both of those to go ahead and find the equation of the tangent plane and the equation of the normal line. So for example 7, find the equations of the tangent plane and the normal line to the given surface at the specified point. So if I want to find the tangent plane, the first thing I want to do is I want to find my gradient of f. So I'm going to go ahead and find the gradient of f. And when I do this, I'm going to go ahead and get the partial derivative of x times a partial derivative of y and partial derivative of z. So the partial derivative of x of my function is going to be, looks like y plus z. The partial derivative of y of our function is going to be, looks like x plus z. And the partial derivative of z looks like it's going to be y plus x. Alright, so there's my gradient, and now I also want to take my gradient in my initial point. So my initial point, again, is going to be 1, 2, 1. So I'm going to go ahead and plug in into that. So my gradient at 1, 2, 1 is going to be, looks like y plus z is going to be 3. X plus z is going to be 2. And y plus x is going to be 3. Alright, so there's my gradient at f. And again, that is going to be my normal vector for the tangent plane at the point 1, 2, 1. And now I have everything that I need to go ahead and write the equation of the tangent plane. So this is A. And the equation of a tangent plane is going to be 3x minus 1 plus 2 times y minus 2 plus 3 times z minus 1, and that's equal to 0. And again, we could solve for that if you'd like. So if we do solve for that, we could say, or 3x plus 2y plus 3z, 3, 4, and 3, 3, 4, and 3 are going to give us 10. Alright, now let's go ahead and find the normal vector. And again, the normal vector is just going to be x minus our initial point, so x minus 1 over 3, y minus 2 over 2, and z minus 1 over 3. And again, that corresponds to our normal line symmetric equations. Alright, so hopefully that wasn't too bad for you. Again, the most important part is knowing the equation for the normal line, and then also, or the symmetric equations for the normal line, and then the equation